Hi everyone, I'm Pratyush and I'm presenting Delphi, which is a system for secure inference on neural networks. This is joint work with my excellent co-authors Ryan, Akshay, Zheng, and Raluca. Okay, so today many applications use neural networks to enrich user interactions. For example, home monitoring devices use these networks to detect and recognize visitors, while baby monitors use this to detect motion in children and to alert parents. Let's see what a secure inference application looks like with the example of the baby monitor. So there are two parties, a client and a server. The client holds some input X, for example, a feature vector extracted from a picture of the child, while the server holds a machine learning model M. The goal of the client and server is to interact in a protocol to eventually derive the prediction of the machine learning model M on the input X, so to get M of X. Now the problem is that in many cases, user data is sensitive and the server's model is potentially secret. So in this case, for example, the client's input X is derived from a picture of a child, while the server's model M could be trained, for example, on private training data, such as pictures of other children. Right? So let's see what one's options are if you wish to deploy secure inference on sensitive data today. The first most straightforward option is to use what's called client-side inference. Here, the server stores its model M on the client's device, and the client can then locally query this model to obtain the prediction M of X. Now, the problem with this is that the clients use the server's model weights in plain. This reveals not only the model weights, but could also leak information about the data that was used to train the model. And this is not hypothetical. There's been a bunch of papers over the past few years that show how to carry out this attack. The alternative is to use what's called server-side inference. This is somewhat the inverse. Now, the server stores this model M on its own device, and instead, the client sends its input X to the server, who evaluates the model on this input and sends back the prediction result M of X. Now, the obvious problem with this is that the server sees the client data in plain. Okay, so what we want is a secure inference protocol. Here, the goal is that the client and server should learn only the prediction M of X and no other information about the other party's inputs. In more detail, the server should not learn any information other than about the private client input X, and the client should not learn any other information about the private model weights M. Okay, so let's see what some prior work on secure inference looks like. The earliest class of protocols are those based on fully homomorphic encryption. In these protocols, the server homomorphically evaluates the neural network over the client's encrypted input. Now, because FHE is a very heavyweight tool, these protocols suffer from performance overheads compared to native execution and are also not able to efficiently support the kinds of operations that are required by neural networks. So to improve upon this, people have developed protocols based on two-party computation techniques. This includes the state-of-the-art GAZELLE. And while these protocols improve performance compared to FHE, they're still quite far from native execution. So ideally, what we want is a protocol that achieves close to native performance while supporting the kinds of operations that are required in neural networks. And this is what we try to achieve in Delphi. In more detail, Delphi is a system for secure inference on convolutional neural network. We achieve standard simulation, semi-honest simulation-based security while supporting arbitrary convolutional neural networks efficiently. What this means is that we improve bandwidth requirements and inference latency over prior work, such as GAZELLE, by orders of magnitude. And our system can utilize hardware acceleration libraries for computing linear layers. And we evaluate all of these on realistic workloads. Okay, we achieve all of this via a synthesis of three kinds of techniques in cryptography, machine learning, and systems implementations. Okay, so let's see how Delphi works. We'll start with a quick recap of what convolutional neural networks are. These are neural networks consisting of alternating linear and nonlinear layers. Linear layers consist of, for example, convolutions and fully connected layers, whereas nonlinear layers consist of activation functions such as ReLU, which is 0 when the input is less than 0, and the identity function when the input is greater than 0. To evaluate CNN, you proceed layer by layer until you reach the prediction. The starting point for Delphi will be the prior state-of-the-art GAZELLE. The key insight of GAZELLE is that they develop specialized cryptographic protocols for each kind of layer. In more detail, to evaluate linear layers, the client uses linearly homomorphic encryption, which allows evaluation of linear functions over a ciphertext. The client encrypts its input X using this LHE, sends it to the server. The server homomorphically applies a linear function L to the input X, and also applies a blinding mask S. It sends back the resulting ciphertext C to the client, who decrypts it and obtains y equals Lx plus S. Next, to evaluate nonlinear layers, Gazelle uses garbled circuits. And this is because garbled circuits are very efficient for bitwise operations like those required by ReLU. The client provides its input y, and the server provides its input and the mask S. The garbled circuit undoes the mask and obtains the linear layer output Lx and applies ReLU, and finally outputs an encryption of ReLU val of x so that the client and server can go ahead and compute the next linear layer in the protocol. Okay, this continues until you reach the end of the network and obtain the final prediction. All right, so Gazelle has spent a lot of time on optimizing each of these components. However, despite all of these optimizations, there's still overhead compared to native execution. In more detail, LHC libraries do not support, for example, GPU acceleration. So it's already much slower than the best techniques for evaluating linear layers. And garbled circuits incur security parameter overhead compared to native execution. And put together, this results in 600 megabytes of communication per inference, and each inference takes 82 seconds to complete, which is unacceptable for latency sensitive applications. Okay, so in Delphi, we tried to lower these requirements by optimizing each kind of protocol. Okay, so first we optimize linear layers by splitting up the protocol into two phases: a pre-processing phase that happens when that is independent of the client's input, and an online phase that is dependent on the client's input. So in the pre-processing phase, the client first samples a random R, encrypts it with the LHC from before, and sends it to the server. The server now samples the mask S, like in the Gazelle protocol, and homomorphically applies the linear layer to LR and applies the mask S. It sends back the resulting ciphertext to the client, who decrypts it and obtains y equals LR plus S. The key thing to note here is that this is almost identical to the Gazelle protocol, except instead of using the actual client input X, we're using a random value R. Okay, this is the pre-processing phase. Then in the online phase, when the client gets its input, it sends it to the server masked by the random value R, and the server can then homomorphically apply the linear layer to this masked value. And the key thing to note now is that the client and server hold a secret share of Lx. The server has z equals Lx plus y, while the client has y, right? We take advantage of this by plugging this into the garbled circuit. So the client provides y and the server provides Lx plus y. The garbled circuit combines the secret shares and reconstructs Ls, and then applies a ReLU to this and outputs a fresh share for the next linear layer operation. Right? And so then the server and client can go ahead and compute the rest of the network iteratively. Okay, so this is great because we're operating over plain text and are thus GPU compatible. And this allows us to reduce both the latency and the communication cost down to 13 seconds and 350 megabytes respectively. Okay, but we still have this bottleneck of the garbled circuit, and let's see what we can do about that. So to optimize nonlinear activations, the first thing to note is that while ReLU is cheap for CPUs, it's not cheap in 2PC. This is because in the CPU cost model, bitwise operations are cheap, but what is cheap in 2PC cost model is arithmetic operations such as multiplications. So a natural idea would be to replace the ReLU with something which is cheap in this cost model. For example, a quadratic activation, where you just apply a quadratic function to the input. Right? This is not a new idea. This has been proposed by the earliest work in the space, such as CryptoNets and SecureML. However, the problem is that training accurate networks which use quadratic activations is difficult because algorithms for training networks are optimized for all ReLU networks. Right? So to work around this, we apply our machine learning techniques. In more detail, we develop a machine learning planner that takes in some accuracy threshold T and a an already trained all ReLU network and outputs a hybrid network which contains a mixture of ReLU and quadratic activations while ensuring that the accuracy is T. The goal of the planner is to maximize the number of quadratic activations and thus maximize the efficiency in the 2PC cost model while ensuring that the accuracy is maintained. We achieve this via a combination of better techniques for training hybrid networks, as well as for adapting neural architecture search to discover these hybrid networks more efficiently. For more details, please see the paper. Okay, so I've told you a lot. Let's see what the end-to-end workflow with Delphi looks like now. So first, the server trains an all ReLU network. Then it asks the client for the minimum accuracy that's acceptable and plugs these into the planner, which spits out a hybrid network, which consists of a mixture of ReLU and quadratic activations. Then the client and server can engage in the pre-processing phase to derive some pre-processing information. And then later, when the client gets his input X, they can engage in the online phase of the protocol to finally derive the prediction M of X. So that's our theoretical contributions. Do these theoretical contributions actually result in practical improvements? So to evaluate this, we implemented a protocol. It's available online at this link. It's a Rust plus C++ library which supports GPU acceleration out of the box. And we evaluated its performance in two metrics. First, the first question to ask is, does Delphi's planner preserve accuracy? Right? Are we getting networks which have high accuracy above the threshold? And second, does Delphi's protocol, when run on these planned networks, actually reduce latency and bandwidth compared to prior state of the art? We evaluate on the deep Resonant 32 network on a moderately hard C400 dataset. This network is deeper than any considered before in the literature. So in terms of planner accuracy, the first question to ask is, are the ReLUs already redundant? That is, could we just replace them with identity functions and reduce the cost that way? And the answer is no. We applied our planner to replace the ReLUs with identities, and what we found was that there would be a massive accuracy loss of over 10%. This is in contrast with the networks found by our planner, which used quadratic activations, where the accuracy loss was only 2%. And this is with replacing 26 out of 32 layers of ReLUs with quadratic activations. Okay. So the next question is in terms of latency and communication of our protocol on these planned networks. The comparison is with Gazelle. And what we find is that in terms of both inference time and latency, we improve by an order of magnitude compared to Gazelle. So, okay, to summarize, I presented Delphi, which is a protocol for secure inference on convolutional neural networks. This is 9 to 22x more efficient than prior work in various metrics, and combines new techniques in systems, cryptography, and ML. The paper is available online, and so is the code. Thank you.